Good morning, all of you. In today's session, we are going to start with the 10th standard chemistry and physics, unit 9, electrical current, series number 2 is going to be discussed. In the earlier session, what are the live examples for the conductors and what could be the reason for the conduction of current and all those topics discussed in series 1 with respect to this electrical current, what is meant by current, and some materials are able to pass and some other may not able to flow the current in that manner. So all these were discussed in the series number 1 of unit 9. In addition to this one, unit number 1 to 8, detailed explanation available on the channel called World of Competitive Chemistry. Now we entered into this electrical current where chemical energy get converted into electrical energy so that can be applied in different fields. Those are going to be discussed. Let us enter into our series number 2. So here we have one question. How does a conductor transfer energy flow? Here, when we switch on, immediately light will illuminate it through the bulb. What could be the reason? Within fraction of seconds, it is possible to transfer the energy and how it is possible. Let us discuss about how the conduction is possible through the wire and how it will be transported to the bulb from the source. Here, in order to explain this, there is a scientific perception which is given by Drude and Lorentz. These are the scientists in 19th century. They gave the what is meant by conductor. So especially with the metals with a large number of free electrons. Already we know metals are electropositive in nature and having more tendency to release the electrons. And they are becoming a positive ions by losing electrons. Ions are not moving, but electrons are mobile in nature and they will transport from one region to another region in the mobile way. The arrangement of positive ions are called lattices. Here it is clearly depicted. Here positive lattices denotes metals which having strong tendency to lose the electrons, so that electrons are moving in such a manner how water is flowing in a pipe. Just like a movement of water in a pipe, here electrons also flowing, and here you can see the lattice structure. Lattice structure is nothing but three-dimensional arrangement of a single unit that will be repeated several times in order to construct the entire metal. So in three possible directions like x coordinate, y coordinate, z coordinate, they will be extended in such a manner so that entire metallic crystal will be generated. In order to get that, the fundamental unit is called a lattice. So these lattice will be extended. These lattice are said to be positively charged and with more mobile electrons on its surface. So that is the reason why here metals are having more prone to conduct the electricity from one region to any other region. And we are going to observe the condition where randomness and also regularity in between electron flow. So that kind of distinction we are going to observe by different kind of conditions. So let us understand the behavior of electrons in the lattice space, how the electrons are moving and what will be the flow of electrons and in which condition they are random in nature and in which condition they are highly regular in nature. We are going to distinguish. Right. So let us understand the behavior of electrons in the lattice space. Assume that conductor is an open circuit. So it will be open circuit. The electrons move randomly in the lattice as shown in this figure. Let us assume this is a metallic lattice where electrons are moving in their own direction of axis. So one is moving in upward direction, any other bottom wise direction, left hand side, right hand side. In all possible directions, electrons having provision to move. This is called a randomness. So as their interest, they are moving in all possible directions. This is random arrangement of electrons when they are present in open circuit. Now, when the electrons are in random motion, they can move in any direction. All possible directions they are able to move. Hence, if you imagine any cross section, so here cross section in the sense imaginary or hypothetical line we are placing. right? So here this is called cross-sectional area. So as shown in this figure, you can observe this is called a cross section. We are going to bisect this entire metal into two equal halves by this hypothetical line. The number of electrons crossing the cross section, the conductor left to right hand side in the 1 second is equal to electrons passing through the cross section from left to right in the 1 second, right? So here we are placing one hypothetical line, right? And we are observing how many electrons are crossing this hypothetical line in a second. So even though they are having provision to migrate in all possible directions, they're always having mobility. That's the reason why some amount of electrons are moving in this direction, left to right hand side. So per second, how many electrons are crossing this exactly is equal to electrons passing from right to left hand side. That means movement of electrons from left to right exactly is equal to right to left, because they are having equal provision of movement. It means net charge moving along the conductor through the cross section will become zero, because left to right, the extent of electrons moving exactly is equal to right to left hand side. The net charge will become zero when the conductor is present in the open circuit. So when it is in open circuit cross section area, the net charge will become zero, because extent of electrons moving in the one direction exactly is equal to opposite direction. Charge cancellation is possible. Now, we are going to arrange these electrons in a particular condition so that movement of electrons are possible. What happens, the motion of electrons when ends of conductors are connected to the battery. So we are taking this conductor, same conductor was taken, and both ends of this conductor now connected with the battery, right? So when ends of conductor connected to the battery, what happens? Electrons are moving in a particular direction. So here, LP denotes what? Low potential. HP denotes what? High potential. High potential means here electrons having the motion towards this left hand side. That's the reason why a potential will be raised in this direction, and these electrons are moving towards the battery, and the battery able to give the electrons towards the low potential in order to make the equilibrium. That's the reason why these are becoming unidirectional. Means all are moving in a single direction, either right hand side or left hand side. That depends upon the potential difference created, right? So because of this motion here, the potential is generated in the highest density. That's the reason why here high potential is indicated. And obviously the end where the electrons are not deposited, are not localized, that will be a low potential region. So here in this moment, in this direction electrons are moving, so they are becoming unidirectional, and also regularity will be assigned for this one when this conductor is connected with the battery. When the ends of conductors are connected to their battery through the bulb glows because energy transfer takes place from the battery to the bulb. The electrons are responsible for this transfer of energy. So here we can clearly distinguish, even though conductor having electrons, those electron mobility will be facilitated by connecting to the battery. Battery is the source of energy which is used to give the instant energy. So that liberated energy will be transformed through the conductor. Then illumination of the bulb is possible within fraction of seconds. So when it is connected to the battery, all the arrangement of electrons are becoming regular, and they are moving in a particular manner without any electricity loss, so that illumination of the bulb is possible. And the electrons are responsible for the transfer of energy from the battery to bulb. So here, the conductor is mainly used for the passage of current rather than generating current. Here, copper wire. After 10 years also, if you are seeing copper wire, that remains as such, because we are not changing its composition. Only we are passing electron through that copper wire. So that's the reason why here conductor used to supply the energy from one area to another. Battery used to generate the energy. Bulb used to glow by gaining this electrical energy. They must have the ordered motion. When the electrons are in the ordered motion, there will be a net charge crossing through the any cross section of the conductor. That's shown in the figure, and the ordered motion of electrons called electrical current. So when we are taking in the open circuit all possible direction, the net charge will become zero, because the possible forward and backward direction will become zero. That's the reason why here, when ordered motion is there, the extent of electrons crossing through the cross-sectional area will become a electrical current. This is a possible definition. This is the ordered arrangement of electrons. Now, thus we can see that electrical current is ordered motion of charges either in positive or left to right hand side or right to left hand side, but the condition is the electron flow should be in a regular manner or ordered motion is required. Let us define the electrical current in the quantitative manner. So this is called the ordered motion of current. So electrical current is defined as the amount of charge crossing any cross section of the conductor in 1 second. So cross section is nothing but hypothetical line which is placed in between the conducting medium. So bisecting hypothetical line is called a cross sectional area. Through that cross sectional area, how many electrons, how extent of charge is passing in 1 second, that is denoted as electrical current. So here is the metallic conductor, let us assume, and we are passing charge. Q denotes a charge here, and hypothetical line was placed so that here how many electrons are, how extent of charge crossing in 1 second through this cross-sectional area is denoted as electrical current. Now, so that can be taken in the quantitative manner. Let Q will be the charge crossing through the cross section of a conductor in a time interval of T. T will be 1 second, for example. The amount of charge crossing through the cross section in 1 second will become Q by T, right? So here Q will be the charge, T will be the time interval we are focusing. Then Q by T is the ratio that will be the charge crossing through the cross sectional area. Now, electrical current in a quantitative way, it will be defined as electrical charge by time required for that passage, time interval we are taking. So electrical current is denoted with I is equal to Q by T. Q denotes electrical charge, time interval is denoted by small t, right? Here, SI units of electrical current will be ampere. So current will be mentioned in ampere and it is always denoted with A, ampere with A. 1 ampere is equal to 1 coulomb in a second. 1 coulomb is nothing but 6.625 into 1018 electrons, 1018 electrons, right? So here 1 ampere exactly is equal to 1 coulomb per second. 1 coulomb is nothing but 6.625 into 1018 electrons. This is a constant value. So in this way, electrical current is taken as the ratio of electrical charge and the time interval. That is I is equal to Q by T. I measured in amperes. Ampere is mentioned with A, capital A. 1 ampere exactly is equal to 1 coulomb per second. Why do electrons move in a specified direction? What could be the reason for this regular ordered motion when they are connected with the battery? So this is a question time. Now let us enter into a deep discussion about this one. When a conductor is not connected with a circuit through the battery, electrons inside the conductor are random in motion. So this is called open circuit, right? So here, when it is connected with the battery, electrons move in the specified direction, either right hand side or left hand side. That depends upon the potential difference. This shows that something causes the electrons to move in the specified direction. When the ends of conductors are connected to the terminals of battery, uniform electrical field is set up throughout the conductor. This field makes the electrons to move in the specified direction. When it is connected with the battery, then only specified moment is there. Otherwise, there is a random motion in all possible directions. In that case, we are not able to get any kind of electricity. And another question we got, why do electrons move in the specified direction? In which direction do electrons move? The electric field point the direction of force, that would be a positive charge. An electron which move in the opposite direction of the electric field because of negative charge. Therefore, it will move in the towards the left hand side. Electric field point direction of force would be in the positive charge, because electricity is nothing but flow of electrons. Flow of electrons always towards the positive end. So here, electron will move in the opposite direction of electric field because of its negative charge. Therefore, always left hand side, these electrons are moving. Being electrons are negatively charged, always move towards the positive end. Do the electrons accelerate continuously? So movement of electrons, is it a continuous process? No. They lose energy and are again accelerated by the electric field. So when they are moving, what happens? At some instance, the complete loss of energy is possible. At the time, acceleration may not be possible. And when they connected to external electric field, again, they will gain the energy. Again, movement of electrons are possible. That's the reason why continuous acceleration of electrons are not possible. Do they move with a constant speed? So here, constant speed is possible for all the electrons when they are passing through the conductor. Let us solve this problem. Electrons, while flowing in a wire, collide with a certain impurities, components of wire, and even result in the acceleration for short while, and its speed suddenly becomes zero. So because of collisions among them, their particles, otherwise with the walls of conductor, otherwise any impurities whichever present in the conducting medium, at that instant what happens, because of collision they are losing the speed, and their net speed at that instant their speed will become zero just after the collision. Hence, we are supposed to take their average speed of electrons rather than individual speed of the electrons. So here we are going to measure the average speed of all the electrons instead of individual speed of the electron, because some instant electron speed will become zero. Some instant electron is moving in a particular manner. Some instant electron speed will become slow and fast. In that case, average speed was taken. So when average speed was taken, that will be a constant. Always average speed of all the electrons will be taken as the constant value only. So if some are moving faster, some other will become slow. So at that instant, the equilibrium is maintained. So here entire speed of electrons will become constant only. So if these electrons are moving fastly and whatever electrons moving slowly, they are maintaining the equilibrium. In that case, always its speed will be taken as the constant only. Right. Why do electrons move in the specified direction? And I collected this answer from Topper answer. Thank you very much for your information. The free electrons in the conductor are accelerated by the electrical field, move in the direction opposite to the direction of field, because always electrons are having negative charge and always having tendency to move towards the positive end. Electric field point in the direction from the higher potential to lower potential. Always any system having tendency to maintain the equilibrium. If high potential is there, that having tendency to move on to low potential in order to make the equilibrium. That's the reason why free electrons accelerates in the direction opposite to that of electric field. Hence, the free electrons move from the lower potential to the higher potential in order to make the equilibrium. That's the reason why here always a specified direction will be there that is opposite with respect to the external electric field. In order to maintain the equilibrium, electron density should be equalized. For that purpose, always they are moving in opposite direction of external electric field. By this, we completed session number 2. Hope the session will be helpful for your preparation. Thank you one and all.